Hey guys, my name is Shreyas and welcome to Simple Chemistry. In this video, in our final video in stoichiometry, we're going to be looking at a concept called limiting reagent. Okay, so if you look here, this reaction is telling us for every one molecule of methane that reacts with 2 molecules of O2, 1 molecule of CO2, and 2 molecules of H2 are created, okay? Now, in this scenario here, let's see. So the little green molecules represent CH4, and the little blue molecules represent O2. So if you look here, for let's say this CH4 molecule, this CH4 molecule can react with these 2 oxygen molecules. So I'm going to draw a little circle like this. So we have that. This CH4 molecule can react with these 2 O2 molecules. This CH4 molecule can react with these 2 O2 molecules, and this CH4 molecule can react with these 2 O2 molecules, okay? So in this scenario, there is no limiting reagent because everything is used up, okay? Now, you don't understand what a limiting reagent is, so when you look at this scenario here, I think you're going to be able to understand. So here, this CH4 molecule can react with these O2 molecules. This CH4 molecule can react with these 2 O2 molecules, and this CH4 molecule can react with these 2 O2 molecules. However, there's still 2 O2 molecules left up. If there's one more CH4 molecule in this box, then those could react too. But since there's not and 2 O2 molecules are left up, CH4 is a limiting reagent. Okay? Now in this scenario, this CH4 molecule can react with these O2 molecules. This CH4 molecule can react with these 2 O2 molecules. And this CH4 molecule can react with these 2 O2 molecules. Okay, if there was 2 more O2 molecules, this CH4 molecule can react, but there's not. Therefore, O2 is a limiting reagent. Okay? So, that's the concept here. Now, sometimes you're going to get problems. You're not going to just like to draw these little circles and identify which limiting reagent. It will ask you that sometimes on the AP Chemistry test, but you might also get something like this. Okay? So let's look at this problem. 20 grams of N2 reacts with 15 grams of H2 to form ammonia. Which reactant is limiting and how much excess is left over? Okay, so let's first, right before we do anything, determine what the chemical reaction is. So we're given that N2 is reacting with H2 to form ammonia, which is NH3. Let's balance this equation now. So we have 2 nitrogen atoms here, just 1, so we can put a 2 here, and then we have 6 hydrogen atoms here, and we only have 2 here, so we can go ahead and put a 3 here. Okay, and now everything is balanced out. So we have 20 grams of N2 and we have 15 grams of H2. It's going to form ammonia. So what we're trying to determine here is which one of these reactants, nitrogen or hydrogen, is going to run out first. So the best way to do this is do the stoichiometry 2 times. 1 time with just the N2 and 1 time with the H2. Okay, and then determine which is producing the smaller amount of ammonia. Once you determine which is producing the smaller amount of ammonia, you know which one is a limiting reagent. Okay, so let's go ahead and do that, and you're going to probably get a better understanding when I actually do that. So let's see how much ammonia, how many moles of ammonia is going to be created, let's say, just by 20 grams of N2. So first you have to convert this to moles. So 1 mole of N2 has a mass of, if you look at the periodic table, nitrogen has an average atomic mass of 14.007. So if you have 2 nitrogen atoms, you can have 28.014. That's the mass of 1 mole of N2. 28.014 grams. Okay, and then from here, the reaction is telling us for every 1 mole of N2 that reacts, 2 moles of NH3 is created. So for every 1 mole of N2 that reacts, 2 moles of NH3 is created. And then grams of N2 cancels out with grams of N2, moles of N2 cancels out with moles of N2. So from there, let's go ahead and do the math. So 20 times 1 times 2 divided by 28.014 times 1. So we're getting this. I don't want to round this down to just 1. Let's say that the 0 is also significant, even though technically it's not, just because we're gonna run into problems if you just round this to 1. So let's just take the answer as 1.4. So 1.4 moles of NH3 is created here in this scenario. Now let's do the same thing, except let's take 15 grams of H2. Okay, so let's see how many moles of NH3 is formed by the reaction of 15 grams of H2. And let's ignore the N2. Let's just say that there's enough N2 to react. So this is the second case. We can call this case 1. Let's say case 1, and then case 2. So we're solving case 2 now. So 15 grams of H2. First convert this to moles. So 1 mole of H2. We know that the average atomic mass of hydrogen is 1.008. So we can multiply that by 2. So that gives us that the molar mass of H2 is 2.016 grams per mole. So 2.016 grams of H2. And then from here, finally, the reaction is telling us for every 3 moles of N2 that react, H2 which reacts, 2 moles of NH3 is created. So we can use that as our mole ratio. 3 moles of H2 that reacts, 2 moles of NH3 are created. Okay, and then grams of H2 cancels out with grams of H2, moles of H2 cancels out with moles of H2, and we're left with moles of NH3, which is what we want. And then, okay, we can just go ahead and multiply all this out. So 15 times 1 times 2. Okay, divided by 2.016 times 3. And we're given this 4.96. So we can round this to 5.0. Okay. So what this information is telling us is that if we had 20 grams of N2 reacting, we can create 1.4 moles of NH3. But if you have 15 grams of this first case is assuming that we have excess H2O. Okay, so if you have 20 grams of N2 reacting, we can only create 1.4 moles of NH3. But in the second case, if you have 15 grams of H2 reacting with excess N2, you can create 5 moles of NH3. So therefore, from this information, since this number here is a smaller number, 1.4, when compared to 5.0, this information is telling us that N2 is the limiting reagent, okay, and H2 is the excess reagent. Let me write that down. N2 is the limiting reagent, and H2 is the excess reagent. Okay, so that's great. Now let's answer the second part of the question. How much excess is left over? So we know that 20 grams of N2 is reacting, okay? And we know that we started off with 15 grams of H2. So what we can do is see how much H2 is going to be consumed by the reaction of 20 grams of N2. And then that information can be used to find out how much excess is left over. We can subtract the number we get there from 15. So let's go ahead and do that. Let's see how much H2 is going to be used up by the reaction of 20 grams of N2. So let's do that in a separate tab. So what we're asking is how many grams of H2 will be used up by the reaction of 20 grams of N2. So first convert to moles. 1 mole of N2 has a mass of, we determined that here, 28.014 grams. And then the reaction tells us here that for every 1 mole of N2 that is consumed, for every 1 mole of N2 that's consumed, 3 moles of H2 is consumed, okay? So for every 1 mole of N2 that is consumed, 3 moles of H2 is also consumed, the mole ratio. And then finally we can convert moles of H2 to grams of H2. So 1 mole of H2, we determined this here, will have a mass of 2.016 grams. Excellent, excellent. So from here, can just cancel out. Grams of N2 cancel out with grams of N2. Moles of N2 cancel out with moles of N2. Moles of H2 cancel out with moles of H2. And we're left with the grams of H2. So this information is going to tell us how much H2 is consumed. So let's say 20 times 1 times 3 times 2.016 divided by 28.014 times 1 times 1. Okay, we're getting this, 4.3. Just say 4.3. So if 20 grams of N2 reacts, 4.3 grams of H2 will be consumed. Okay? Now, we started off with 15 grams of H2, and all the N2 is going to react, and 4.3 grams of H2 is going to be consumed, so what's going to be left over? Very easy. All we have to do is take 15 and subtract the 4.3 grams which is consumed, and we will get 10.7 grams of H2 left over in excess. Okay? And this is our answer here. So that's it for limiting reagent. If you're able to just think logically and use this case of breaking everything down like this into separate cases, as well as being able to identify the limiting reagent and the excess reagent like we did here, and then using that information to calculate the excess reagent like we did here, you're going to be well off for solving limiting reagent problems. Limiting reagent problems are as simple as that.